Hi, everyone. Welcome back. Over the last 8 weeks, I've received countless requests here on my YouTube channel about what kind of videos you'd like to see. Some asked for electromagnets, some wanted to see transistor experiments, and some wanted to see perpetual motion debunking videos. And one of you asked me what my opinion is on the Newman motor. I looked into the subject, so in the end, I chose this. We're going to talk about the Newman motor now, because it covers a lot of things. It covers the electromagnet topic, it covers the transistor topic a bit, and the perpetual motion debunking topic. It's very simple, spectacular, completely harmless. You can learn a lot from it, so let's start learning. I'll bring the camera closer. I've drawn a few things on my whiteboard. I drew two types of Newman motors. You can see one here and the other one here, and this is what our little Newman motor will look like. Now I'll show it to the camera for a moment. There are two coils. Here's one coil, and here's the other coil. You can see these coils here. Here's a coil, and here's another coil, and the way I drew it means that they're coupled to each other. That is, the two coils are close to each other, so the magnetic field of this coil can influence the voltage induced in the other coil. In both solutions, I mark these coils the same way. They are coupled together. I mark the beginning and the end with a dot. So you start winding the turns like this, and let's say, for example, you wind it in the direction of the clock's hands. So this is the beginning, where you started, and logically, where the coil ends, that's the end. And if you keep the direction the same for both coils, let's say you wind both in the direction of the clock's hands, then you can designate this point as the start, and if you wind the other one the same way, then this will also be the start here. This motor runs on 9 volts, so you always need to have a 9-volt battery connected. There's a transistor inside. The exact type of transistor isn't really important. The main thing is that it should be an NPN transistor. This BC182 is very common and very cheap, the 2N2222 as well. Any similar transistor will work in the setup. This is a diode here, the 1N4001 type. It's a very common, very simple, very cheap type. The same kind of diode is used here as well. The whole point of this is that there's a 9-volt battery here. It draws X amount of power from it, and you can get Y amount of power out here, and Y is greater than X. Newman started experimenting with this thing in 1979 and tried to patent this solution. The U.S. Patent Office rejected it on the grounds that there is no device that takes in X amount of energy, outputs Y amount of energy where Y is greater. So there is no device from which you can get more energy out at the output than what you put in. This other circuit diagram is very similar to this one, with the only difference being that you need two AA-sized batteries here, two 1.5-volt batteries. You have to turn the switch on, this charges the capacitor, then you can even turn the switch off, and from that point on, the device draws energy from the capacitor and recharges the capacitor and moves forever and ever. But before I take away the whiteboard, let's take a quick look at the transistor. I know this is a very simplified explanation of how it works. It can be explained in a much more sophisticated way. I'm only doing it this way here so that if someone doesn't know what a transistor is, it's enough to know that if you run current into the so-called base of the transistor, as a result, you can basically turn the device on. It will be almost like a wire, so it won't be a complete short circuit, but there will be a small voltage drop here. Of course, this is true if I use the transistor in switching mode, but if we don't let current flow in here, then the whole thing's like a big open circuit. Naturally, as I said, much more sophisticated explanations could be given for this. Maybe one day I'll get around to making a video where I explain how a transistor works. All you really need to know is that if I apply voltage to the base, or Cu, it starts to conduct, but if I don't supply current here, or there's no voltage here, then this device doesn't conduct. Based on this, the way this circuit basically works is that if this coil can somehow provide about 0.6 volts to the base emitter here, then this device turns on. If this device turns on, this transistor, then current will flow along this path, like this way, but there's also a rotating part since this is a motor. What I have here in my hand is a bicycle seat, and I've attached two magnets to the bicycle seat. This will be the rotating part of the motor, and the rotating part will spin here between the two coils. To understand how this whole thing works, I think it will be much more useful if we take a look at this gadget, at these two coils, and at the rotating part, as well as the little electronics, and then we can actually get it up and running. On this board, you can see the Newman motor, this version that's right here. This coil, the upper coil, is on top in the diagram, and the lower coil, which is here, is at the bottom. The lower coil consists of 250 turns. Between the coils, there is the same kind of rare earth magnet as this one. Take a look. It's so strong that if I start turning it here, I don't know how well you can see it, but I can actually move the shaft of the Newman motor. You can see that I put a small disc here, so the distance here is about 10 centimeters, and across this 10 centimeters, you can transfer enough magnetic energy that the shaft of the Newman motor move it. See? I'm turning the magnet here in my hand, and the shaft of the Newman motor is turning as well. But it doesn't become a perpetual motion machine just because I spin this under the table or behind the whiteboard. It's for a completely different reason. Or rather, it's not for that reason at all. So it has a rotating part. And here I've drawn a propeller. The propeller ended up on a small wooden disc. You can see the transistor circuit here. It's really very simple to wire up. Here are the 4 wires. This is the emitter of the transistor. This is the base, which connects to the lower coil, which has 250 turns. And this is the collector of the transistor, which connects to one end of the upper coil, specifically the beginning. Here is the diode. And don't forget, there's also a capacitor connected here, which you can see. This is where the Newman motor will generate energy, and the whole device is powered from this capacitor as well. And here in my diagram, I have 2 cells marked as 3 volts. I did not have any batteries right now, so I am going to use a rechargeable battery of the same size. And to set this whole thing up, I will turn it here. I brought a clip, and I will connect the brown wire to the brown wire here. This right here is the negative pole of my battery, and I'll just hold the red wire here for now, so nothing happens yet. You actually have to give it a little push first. There's a little propeller drawing, and now it's not just a simple line, but a kind of blurred circular path or something like that. Maybe now you can see it clearly on the screen. This whole thing really works exactly as intended, and actually, it works just like I described earlier in the drawing. The transistor is switching on and off repeatedly, and the reason it does that is because a specific voltage is generated in the coil at its base, and the rotational energy is provided by this upper coil here, which is this one right here. And the motor begins to rotate because from time to time, this transistor switches this coil on, so current flows through it at regular intervals. The magnetic field of this current interacts with the magnetic field of the magnet in the rotating part, and from that point on, the whole thing really spins. It actually functions quite well. I'll show it to you one more time. The device is quite a bit noisy, but I hope you can still hear exactly what I was saying. There are no tricky components or switches inside. I didn't hide a 1,000 kilowatt transmitter under the table, so this really works as shown. There's only one tiny cheat in it, and I'll show you the trick right away. I just need to put this on something soft so that when I speak, it doesn't interfere with the microphone. This will be the soft thing. I hope it dampens the vibrations a bit. I didn't write anything next to the capacitor here. I just indicated that there's a positive terminal and a negative terminal. This is what a capacitor looks like, an electrolytic capacitor, here in my hand. The negative terminal is marked with a stripe like this, and usually nothing is marked on the positive terminal. The capacitor usually has its specifications written on it. I'll try to hold it so it's readable, maybe like this. Maybe you can read it. This one is 16 volts, 1,000 microfarads. Let me show you another capacitor. This one's a bit bigger. This capacitor is 63 volts and 1,500 microfarads. What exactly do you need to know about capacitors? They can store energy, which is also utilized by the Newman motor, and more precisely, they can store electrical charges. The charge Q is equal to the capacitance C multiplied by the voltage U. This is sometimes called the Kuchik-Kettlet formula, where Q is the charge and C is the capacitance of the capacitor. For this specific capacitor right here, that's the 1500 microfarads, and U represents the voltage to which we've charged the capacitor. With the two rechargeable batteries, I actually couldn't charge it up to 3 volts, only to about 2.8 volts in total, so here U is 2.8. And what about C? It's very important. Let me show you again. As you can see, the value was actually specified in microfarads here. Now let's take a look at the capacitance value of the capacitor. This is also measured in microfarads. Let me show you the actual capacitance of this specific capacitor right here. Well, I really hope you can see it clearly on the screen. This is a 2.8 volt one. Maybe if I hold it like this, and I hope you can see it, it's exactly 22 farads. And this time I definitely didn't mess up the unit. It's not microfarads, but actually 22 full farads. There are 22 farads right here, and everyone can easily multiply that out. It's an insanely large value, what we have here. This is basically a high-capacity battery that ended up here. We're not talking about microfarads, but very serious farads. So this whole setup basically runs entirely off this capacitor. I'll also show you the actual voltage of the capacitor. I brought a digital voltmeter here specifically for that. By doing it this way, maybe the display won't glare as much. The motor is actually running off this 1.6 volts. However, the voltage in the capacitor is continuously dropping, so the rotation speed is also gradually slowing down. But it keeps running for a very long time. I went ahead and checked it, and if I charge this capacitor up to 3 volts, and as a result, this whole little device runs for an additional 20 to 25 minutes. If there were better bearings here, it would probably run much longer. And you could also use a better transistor or a better diode, so it could actually work for quite a long time. So if someone presents a perpetual motion machine like this, showing it working while they keep talking, it might look real, but in reality, it doesn't actually work. In other words, it doesn't operate in perpetual motion mode, but rather it draws its energy from this capacitor here. You have to give it a push. No matter which direction you push it, whether to the right or to the left, it'll start spinning in either case. It's seemingly perpetual motion, but in reality, it's not. It's a really fun, cool little device, and it can actually run for half an hour, or 20 to 25 minutes. There's still that same electrical charge in the capacitor that I put in just for a brief moment right at the very beginning of the experiment. You can optimize quite a lot of things on it. It could even become a believable perpetual motion machine. But that wasn't the point here. The point was to get to know a few simple things. Here, the magnetic field of the electromagnet was constantly pushing the rotor. The rotor didn't need any commutator. This transistor simply switched the magnetic field of the stator on and off for a moment with the appropriate periodicity. And the transistor switched the current to the coil exactly when the rotor had to be pushed past the dead center. And the pulses kept coming here. These were constantly pushing the rotor. The rare earth magnet placed on the rotor induced voltage exactly when it was needed, when it had to be pushed past the dead center. As far as I know, the Newman motor has not been patented to this day. In 1980, many applications were filed for it to be accepted. They were always rejected, saying that the output energy cannot be more than the input energy. By the way, the upper circuit diagram works exactly the same way as the lower one, in the sense that it will stop after a while. It will stop when the power runs out of this 9-volt battery. From then on, the whole device won't work, since the motor consumes very, very little, so this 9-volt battery can operate the little device for even hours. I hope you like my video. Come back another time. I'm always happy to have you. Bye, everyone.